Hello everybody, welcome to Math 127 at Christopher Newport University. Today's screencast is going to be on what's called RSA encryption, which is an example of public key cryptography. Today's screencast, we're going to be using the slides quite extensively, but also we are going to be using Mathematica as well. So you probably want to have Mathematica up and running with the MCP evaluated. Also, we are going to be using what I'm going to refer to as the RSA scheme. If you haven't, you may want to download this from Scholar as well and evaluate this notebook much like you would the MCP. Make certain you do the MCP first because this depends on the MCP being loaded. All right, so let's get started. Okay, so to date, in this class, all of the crypto systems that we have been looking at have been what are referred to as symmetric ciphers. Both parties or all parties are in possession of all information that is necessary. Okay, so they know what type of cipher they're using, they know how the cipher works, and they all know the keys. Also, as a part of that, knowing the encryption key allows you to determine the decryption key. In some cases, it's obvious, if you're adding your key, then you just subtract it. But in other cases, if you're multiplying by the key, then you know how to find the inverse. So we're going to switch gears and look at what's now referred to as an asymmetric cipher, or sometimes also a public key system. In this, every user has two keys. They have a public key and a private key. And I should stress that the user has the keys. So the key itself is dependent upon who is using the system. Now, you have multiple users in the system. There are these public keys, and they truly are public keys. Everybody in the system knows or has access to all of the public keys, but only each individual user has access to their private key. On top of that, knowing a public key doesn't allow you to determine a private key. So that's a big difference between a public key system and a private key system. All right, so as a first example, let's say Alice wants to be able to have anyone in the world communicate with her privately. So she puts up onto her website the following information. If you want to contact her, you're going to take your message, convert it to Unicode, put it into blocks of length 4, just like we did for the exponential cipher. And then you're going to use an exponential cipher. But what she does, she gives you the encryption key, which is this very, very large number. And she also gives you the modulus that you're to use. She lets this out freely. Anybody can access this information. Okay. So Bob on the other side of the world wants to send a message to Alice, and he's going to send the message, "I would like to eat your suitcase." And if you get that reference, then you have knowledge of very obscure movies. Okay, so that's what he wants to do, so he's going to do as instructed. Now, one of the things about those values that Alice gave, those things are huge. He's going to need pretty serious computational power to do it, so big surprise, off to Mathematica we go. Okay, so Bob is going to follow the instructions that Alice gave. He's going to take his message and he's going to prep it just like we have for the exponential cipher. All right, so he's going to convert it to character code and then he's going to block it and everything. And I'm not actually going to record this section. I'm just going to pause it for a moment and then everything will be perfect when it restarts. Okay, so here is the message now padded appropriately and then blocked to use an exponential cipher. And so I'm calling it play code for short for plain code. All right, and then he takes the plain code, he raises it to the key that Alice published and reduces it the modulus she provided, and he gets a ciphertext. All right, so Alice needs to decrypt that. So she receives that whole string of numbers. Now she let the encryption key out. She needs the decryption key, which she happens to know. So she's going to go through and decrypt it just like an exponential cipher. So she would use her decryption, and she would take what was sent to her and she'll raise it to her decryption key. She will then reduce it modulo the modulus she required, and she will get that, and then she would break that apart accordingly. But if you notice, these numbers and these numbers are the same, so she will indeed decrypt what Bob sent her, strange though it may be. Okay, so is it secure though? Because after all, she let out her encryption key. We know in theory how to find the decryption key for an exponential cipher. If I'm using this as my encryption key, then the decryption key is simply the inverse of this number modulo the Euler phi of this number. Okay, so Eve comes along, she intercepts the message, she has everything that Alice has left out there, so she needs the Euler phi and then the inverse. Okay, but in order to compute the Euler phi, she can check to see if this is prime. That's going to take a very long time with a number that size. It's not prime. So she needs to factor it. Yeah, that's not happening. Not with a number that size. So even though she knows the encryption key, and even though she knows the modulus, she's run into this very difficult problem. She has to factor this gigantic number, and she has no idea how to do it. All right. I would also point out, while we're thinking of Eve is an attacker. Bob isn't an attacker, but Bob is in the exact same position. He has the exact same knowledge. He knows the encryption key. He knows the modulus. But even if he wanted to, or if he was allowed to, he cannot work out Alice's decryption key. All right, so this first example is an example of what's called a public key crypto system. This key was public. Alice knows it. Everybody knows it. But then there's also a private key, her decryption key, which only she knows. This was an example using only 2 players. In reality, we need ones that work for larger numbers of players. So enter what's called the RSA encryption scheme. Okay, RSA comes from Rivest, Shamir, Adelman, the people who first discovered this or constructed it. They were in response to Diffie-Hellman's paper on new directions in cryptography, where they put out this challenge. And what happened was Rivest and Shamir started working on this, and they came up with an idea, and they took it down the hall to Adelman, and they showed it to him, and he showed him that it wasn't secure. And so they went back to their offices, they tried again, they came down to his office, and Adelman showed him, nope, it's not secure. And this went on for something like 30 to 40 iterations until they finally came up with a viable option. Now, while RSA came out in 1978, we have learned recently through declassified documents that the British Secret Service basically had a version of RSA. They never implemented it, but they had worked out how it would work. Okay, so when you're doing an RSA encryption scheme, there's 2 sets of players. There's what's called the Central Encryption Authority. They're going to set up the scheme, all right? And then there are the people who are going to be using it. Now, the Central Encryption Authority, they are going to decide on a modulus n. What they do to find n is they look for 2 really large prime numbers. Now, in this day and age, we are talking literally hundreds of digits. So they find these 2 large prime numbers, and n is going to be the product of the 2. So in real life, they find p and q, multiply them, and get n. They don't find n first. They go the other way, find the components. But then p and q, since they are distinct primes, computing the Euler phi is reasonably straightforward. It's just p minus 1 times q minus 1, and it's easy if you know p and q. Now, for every person in the scheme, the CEA decides on two numbers: the encryption key, E sub p, and the decryption key, D sub p. These are going to be inverses modulo the Euler fee. Now, they are in possession of the Euler fee. They can work that out without any difficulty. All right, then Central Encryption Authority sends out certain information. Some information is purely public. N, the modulus, that is public. All of the encryption keys are public. They just publish a roster of them with the user and their encryption key. Then, private knowledge, to each individual player, they're going to give them their decryption key. All right, so every person can see all of the encryption keys, but each person only knows their own decryption key. The other thing is that the CEA keeps two things sacrosanct and secret. N, how it factors in particular. N is allowed out, but its factors are not. So you cannot have P and Q released, nor can it release the Euler fee. It keeps those two values secret at all times. Okay, now with all of this information out there, how does it actually work for communication? Okay, so Alice wants to send a message P to Bob. All right, well, she just looks up his encryption key. She knows it's an exponential cipher. She knows the exponent to use. She knows the modulus. So she just takes P, raises it to the correct key. That gets the encryption and sends that to Bob. And then Bob's got the decryption key. It's an exponential cipher. It's the inverse of E mod the Euler fee. So he just decrypts it using his decryption key, and all is good. Now, a couple of things to note about this. Alice never has to arrange anything with Bob or any player in the system. Okay, so anybody in the system that she wants to communicate with, she just has to look up a key. She doesn't have to contact them privately. She doesn't have to have any communication with them other than the encrypted message she sends. The other thing is that while, again, they may know the encryption keys, they have no idea what decryption keys are. Because N is large and the Euler fee is secret, there's no way that they can recover that information in any sort of timely fashion. Now, on the other hand, if Bob needs to reply, he's going to look up Alice's encryption key. So the encryption key is going to change depending on who you're sending it to. But that's okay. That's easily done. All right, so if he wants to reply, he's going to look up Alice's encryption key, encrypt whatever he has to send, and send it back. Now, why is it secure? Again, I've already mentioned this a couple times, but it bears repeating. N is public, but P and Q, its factors are not. And the things are huge. It is a general hard problem in mathematics, given a large number, how to factor it into primes, especially if the prime factors themselves are large. Okay, so that's good for us. And again, anybody who's on the outside of this system, they can intercept any ciphertext, but they need the decryption key. They cannot find the decryption key without finding the Euler fee. They can't find the Euler fee without having the factorization, and the factorization is ludicrously hard to find. You might try other sort of brute force approaches, but again, with the size of the numbers involved, it's just too computationally intensive to work. The other thing about it is that this system is dynamic. Because there's no bound on N, we can find primes as large as we like. As computers get more powerful, it doesn't matter. We just increase the size of N. All right, so we can outstrip technology as it sort of advances. We can advance with it. Okay, so we are going to set up an RSA scheme for this class. I am going to be the Central Encryption Authority. You guys are going to be the players. Now, how is this going to work? Well, frankly, there's one little subtlety I haven't quite worked out, but we'll get there. Okay, so if you haven't downloaded this notebook, you probably should. And after you've loaded and evaluated the MCP, you want to evaluate this notebook. Now, it is going to go through, it has every person in the class. I have updated some of your names because some of you go by shortened names. If I've missed you, I'm sorry, I apologize. I left everybody's middle initials because it was too annoying to try and edit it manually. There are some things that go on in this notebook that are part of setting up the process. They have nothing to do with what you're going to do. This is one of those commands. Don't worry about these things. So we're going to use a modulus. We are going to use this number as our modulus. It will load into memory as RSA mod. Okay, this is the product of two very large prime numbers that I am not going to tell you. All right, now, in order for this to work, we have to generate a whole bunch of keys, both public and private. The public keys are generated in here. I've closed this cell. You can open it if you want. It's just this gigantic list of numbers that I need there. The private keys are not there though, so don't think that you can get it. All right. Then we need a roster. And there they are. Everybody's public key. So if you want to communicate with anybody in the class, these are the public keys you're going to use. Note there is one for me as well. Now, that means everybody needs their private key. That is the small little detail I am still working on at the time of this screencast. I have generated your private keys. Normally, I just distribute them in class one day. That is not possible. So you are going to receive a notebook from me, probably via email, which is going to have your name, your public key, your private key. It'll also have the modulus value in there. Do not lose that notebook. You are going to need your private key. Generating keys takes time. So if you misplace your private key, it is going to be a lot of work for me to regenerate it. So do not lose your private key. You are going to need it on exams. You are going to use it on exams. Without it, you will lose points on exams. I say this every semester, and every semester there's somebody who loses their private key. It drives me nuts. Okay, anyway, but this is the roster of all private keys. Sorry, public keys. All right, as I said, I've got a key, it's in there. This is the command that will do the RSA encryption. Now, all it is an exponential cipher. So you could do it with the exponential cipher commands, but since we're always using the same modulus, it's built in, and all you have to do is give it a message and give it the key. It will encrypt and decrypt. If you give it a string, so set of text, it's going to encrypt it. If you give it numbers, it's going to decrypt it. It will decide which one is which and take care of the problem. Okay, so let's see how this works. Now, because this scheme is working for people in the class, I have chosen some of you to be subjects of messages. I hope you won't be offended, but I doubt you will. Okay, so as I mentioned, that is the value we're going to be using. You don't need to memorize that or anything. It's in the RSA scheme notebook, and it will be in the notebook that I distribute to you with your private key. Okay, so let's say Alice wants to send Go Blue to Dale. I probably wrote these notes while watching a Michigan game. Okay, so she starts out the same way as always. She's going to take Go Blue, she's going to turn it into Unicode, she's going to pad everything as necessary, and put it into blocks of length 12. Okay, that's what she ends up with. All right, so then Alice would go to the roster, and she would look up Dale's public key, which is right here. Okay, so in theory, she would take these two numbers, once she has Dale's public key, and she would work out those two computations. All right, well, for us, this is a little easier. We would use the RSA command. We give the message. We give the public key for the person who's to receive it, and there is the ciphertext. Okay, now we get the ciphertext as mentioned. Great. Decryption works exactly the same. You would take the ciphertext you receive, you put it into RSA, and you raise it to the private key. Now, for an example, I can't show you one, because if I did, that would show somebody's private key. They've got to remain private. So you're not going to see an example of that. One of the worksheets that I'm going to give you, you're going to communicate with each other, and you're going to get practice using your private key. Make certain you understand how it works. As I said, it's the exact same command. It's just RSA, the list of numbers that's the ciphertext, and you put in your private key, and it will decrypt perfectly. Okay, so that's how a public key crypto system works. Now, unfortunately, while there's a general increase in the amount of convenience, i.e. you don't have to have individual parties setting up private meetings and so forth to establish these things, there is one sort of problem that comes out with public key systems. All right, when you're looking at a private key crypto system, when Alice receives some ciphertext from someone who calls himself Bob, then she decrypts using the decryption key, which is private, that she and Bob had agreed upon. In theory, only she and Bob know that key. Okay, so if it doesn't decrypt into something sensible, then she knows the message is non-authentic. She knows that somebody is impersonating Bob. All right, on the other hand, if it decrypts as sensible text, then the sender had to be in possession of the encryption key, which is private. So, as long as they've been maintaining decent security, Alice can be reasonably certain that the sender was Bob. Knowing the private key is an authentication on the sender. All right, now, in a public key, then things change. So Alice receives her ciphertext, and Bob says he sent it. So she decrypts it using her own private key, which Bob is not in possession of. Well, so if she decrypts it and she gets sensible text, unlike before, that doesn't tell her anything. All it tells her is that the sender was in possession of her public key. So it could be Bob or it couldn't, because everybody knows her public key. And, if it happens to decrypt as nonsense, well, then the person who was doing it was an idiot, because public key is available. They just didn't use it properly. Okay, so we need to come up with a digital signature. So Bob wants to send a message to Alice, but Alice needs to be able to authenticate the message and be certain that it came from Bob. Okay, so if we were in class, I would ask you as a group how to solve this problem. Very rarely somebody stumbles across the idea the first time out, but then the clue I always give people is, okay, go back to the science fiction trope where people have switched bodies, and how does the person who's been switched let people know that they're in the wrong body? They always do the same thing. They always tell something only they would know. So, Bob has to send something to Alice that only Bob knows. Okay, there is an immediate sort of candidate for that. It's not the private key. Okay, he cannot send that for two reasons. One is that it's insecure. He's trying to keep that private. If he does send his private key out, somebody is now in possession of his private key, and that's bad. The other thing is that it's actually unrecognizable because it's private. If he sends his private key to Alice, Alice has very little way of knowing that that's actually the private key. Well, she could test it. But he's got to hold his private key. So he can't send the key itself, but he needs to send something that uses his private key, that incorporates it somehow, that allows Alice to verify that it is indeed Bob who sent the message. Okay, so the thing to notice with the encryption keys and the decryption keys in RSA, okay, they're based on an exponential cipher. So E and D are inverses mod the Euler phi. So if I take some piece of plain text and I raise it to the encryption key, and then I raise it to the decryption key, I get the same thing back. But if I'm raising P to the E times D, that's same as P to the D times E, which is same as P to the D raised to the E. Okay, so what does that mean? Well, E and D play interchangeable roles here. We just decide that one of them is going to be the encryption key and make that public, and the other one will be the decryption key and make it private. We could have reversed them. There's nothing special about the two values. Either one can be used as the encryption key or the decryption key. I just have to make a choice. Okay, well, that is going to solve our problem for us. So, what we do for a digital signature, Bob decides on a signature that's going to accompany the message. He has to do two things. The message has to remain secure. The signature doesn't. The signature is just that. It just says who he is. There is no other information in it. So he will encrypt the message using Alice's public key. That gets him the ciphertext, which he sends to Alice. Then he takes the signature and he encrypts it using his private key. So he takes S, raises it to his private key. That gives him a signature file. Now, this can go out again because this is hard to solve. Somebody in possession of T cannot recover the decryption key. So, Alice is going to receive those two pieces of information. She receives the ciphertext and the signature file. She can decrypt using her private key. This is secure, this is private. To authenticate, she takes what Bob sent her and she pulls his public key. She raises that to the public key, which should counteract encrypting it with the private key, and she should get the signature. Now, the advantage here, if the signature comes out and makes sense, then whoever encrypted it had to be in possession of Bob's private key. So, again, if they're maintaining reasonable security, the only person who has Bob's private key is Bob. So, if this decrypts nicely, she knows that Bob sent it and she can be certain. All right, so let's see how this works. So, I am going to send this message ostensibly to Shelby. All right, so Shelby receives this message here, this massive string of numbers, and then accompanying it is this signature file. All right, so Shelby is going to want to decrypt this using her private key, and then she's going to look at this, and she's going to verify that it came from me using my public key. Okay, so she decrypts using her secret key. And again, I can't show you that because that would expose Shelby's secret key. But when she does it, she gets the message from me that says, everybody gets an A. All right, well, can that possibly be true? Well, let's find out. Okay, so I have discovered that there is a small glitch in the RSA command. I'm not quite certain what it is. I have an idea, but I'm going to need to fix it. That being said, everything I've shown you is working. It's just somewhere in the interstices of the command. So I'm going to cut this video off at the end of digital signatures, and then I will, once I have fixed the command, show you how it works in a separate video. Sorry for the inconvenience, but well, welcome to technology.